Everyone, I am Yayati and I'll be presenting our paper on network analysis of Indian corporate interlocks. Here is the here is the outline of the presentation, introduction including related work, followed by the details of the dataset and data pre-processing, and then analysis and finally conclusion. India is the fifth largest economy in the world with a GDP of $4.1 trillion. If you look at the Indian corporate network, corporate environment, it is pretty distinctive. So there are some unique things which contribute to it. So first is the rich heritage and diversity in the country, which drives its business culture. And second is a less regulatory corporate environment, which is more transparent, that allows for a rich corporate interlock network. So at this point, I would like to define what a corporate interlock network is. So as a toy example, it can be represented as a small graph that you see in the figure over here. So it's a small bipartite network containing two kinds of nodes. The gray nodes here are the company nodes, which represent firms, businesses, or organizations. And the purple nodes are the people nodes, which can be executives or CEOs that sit on the board of directors of these companies. So as an example, in this figure, P1, P2, and P3 sit on the board of C1. P3, P4, P5, P6 sit on the board of C2. And an executive like P3, who sits on the board of multiple companies, like P3 is on the board of C1 as well as C2, act as an corporate interlock, leading to the collaboration between these two companies and also information flow, which directly or indirectly impacts the decision making processes. So because of this kind of collaborations created by these interlocks, corporate interlock networks are very well studied for almost all the major economies of the world and a lot of other countries as well. So although here this toy example is a small graph, when you actually visualize it for a bigger network, it looks the graph looks something like this, the one that you see on the left hand side. So it's a small subgraph of the Indian corporate network. The blue nodes are the company nodes and orange nodes are the director nodes. And we cannot study this network by visualizing. Definitely, we require the network science tools to analyze this network further. So that is what we intend to do. So some of the major objectives of our study are to study the structural properties of this bipartite network, to identify the central directors and the central companies, study the connections between them, and at the end, study the sectoral markets. So for each company, we have the data about to which sector it belongs to. As an example, it can be manufacturing, trading, business, finance. So once you have this information, we wanted to study the intra-sector and the inter-sector connections and how this entire corporate landscape in India is shaped. So, talking about some related work in this direction, so for India, this work has been pretty limited. We have been able to find a few studies, a few publications that have studied this network in the past, but most of these studies are small scale and they study like around 1,000 companies. So these are some of them. And talking about on an international level, so as I told, such networks have been studied for the major economies with some very interesting results. So as an example, for the US corporate network, it was shown that in 19th century, there was something like the core of a network or a small inner circle that was responsible for controlling the network, which actually vanished in the 20th century. So many such interesting results have been shown for other economies like Italy and Germany as well. So our aim in this work is to do a similar analysis for the Indian corporate landscape. So here is the details about our data set. So our data set, we have picked up the companies which are listed in Bombay Stock Exchange, which is one of the biggest and the oldest stock exchanges in India. Our data has around 4,600 companies and around 25,500 directors. So this information is obtained from Bombay Stock Exchange as well as a number of other online platforms. And the timeline of this data is from 2004 to 2018. This figure on the right hand side shows the degree distribution of the bipartite network separately for each kind of node. So as you see here, the orange nodes are the director nodes and blue nodes are the company nodes. So this outer curve here, the orange one. So for this, the x-axis is the number of companies, number of boards on which a director sits, and y-axis shows the number of directors. So as you can see here, almost like 90% of the directors sit on the board of only one company, and these are the remaining 10% of the directors, only a few in number, that are responsible for creating these interlocks. This inner plot, on the other hand, is for the companies. So here the x-axis shows the board size and the y-axis shows the number of companies having that particular board size. And just like the previous curve, it also resembles a scale-free degree distribution where most of the companies have a smaller board size and there are a few companies which have a pretty large board size. Now, this visualization that I have shown you earlier, it is not the complete bipartite network. It's a small induced subgraph on that network. So the original bipartite network that we have is actually disconnected and has a lot of connected components. This figure on the left hand side shows the size distribution of these connected components on a log-log scale. So as you can see, around 2,000 components have size less than 100, and there is one big giant component of size more than 10,000. Now, if you look at this giant component, it is not as giant as is observed for other major economies. So mostly in complex networks, giant component occupies like more than 70 or 80% of the nodes. But in our case, this giant component is shown to have 51.5% of the nodes in the network. But still, this giant component is a very good specimen of the original network, in the sense that if you look at the degree distribution of this giant component, it pretty much resembles the degree distribution of the original network. Furthermore, if you look at the sectoral composition of this giant component, so on the left hand side is the sectoral composition of the original network, showing what fraction of companies are from each sector, and on the right hand side it is for the giant component. So it's also pretty much similar. Furthermore, if you look at the most highly boarded companies and the highly boarding directors, all of them come from the giant component. So therefore, for the further analysis, we have restrained to the study of the giant component itself. So to study this giant component still is a bipartite network. So to study it further, we have created two projections of this network separately for the company nodes and for the director nodes. So as an example, let's say there are two company nodes, CI and CJ. And these two companies, they might have some shared directors. Let's say CI is having D1 and D2, and let's say D3 on its board of directors, and CJ is having, let's say, D1, D2, and D4, D5 as the board of directors. Now, in the projected companies network, since CI and CJ have shared directors, there will be an edge from CI to CJ, and this projected network is weighted based on the dice coefficient of the neighbors of CI and CJ. So we have used dice coefficient here because the network is sparse, and this intersection for NCI and NCJ for most of the companies is pretty small. So in this way, we have created the projected companies network. In the similar way, we have also created the projected directors network, and these are the properties of both of those networks. So the number of directors in the projected networks falls down dramatically. As you can see, the average clustering coefficient of the directors network is pretty high. And if you look at the average path length of both the networks, it is small, showing them to be the small world networks. For further analysis, we considered these projected networks. One of the analysis that we have done is finding out the most central companies. So we have actually used a number of centrality measures like degree, betweenness, strength, closeness. But here you can see the paper for more. But in this presentation, I have shown the highest degree and highest betweenness nodes based on the companies. Now, the companies which are shown in star here, they are the family owned businesses in India. And as we can see, most of the highest degree and highest betweenness companies are family owned businesses, which are very common in India. So to look at this further, to study what is happening in this network, we drew an induced subgraph on the highest centrality companies and the highest centrality directors over here. So we have anonymized the directors with an identifier. What we observed was there were not, this is not a very dense network. So you do not see a lot of connections between the highest highest central companies and the highest central directors, which resembles what happens in the US economy, that there is no particularly inner circle which is sort of controlling the entire network. Moving on further, the last part of our analysis is the sector-based analysis. So we wanted to see whether there is a sector-based homophily in the network. What we actually observed is that there is, in fact, you can say sector-based heterophily. Around 15% of the edges in the company's projected network, they are intra-sector, and 85% of the edges are those which run across two different sectors. So to capture this further, we define these three metric here in this plot. So phi of x here is the fraction of companies for the given sector X. Phi I of x is the fraction of companies which are interlocking for the given sector S. And mu I of x is the degree of interlocking, which is sort of division of the first two metrics over here. So the bars over here shows the fraction of companies in a given sector, and this red line over here shows what fraction of them are interlocking. And we have seen that almost all the sectors show a very high degree of interlocking, which is more than 50% for every sector and goes as high as 72% for some particular sectors like manufacturing. So to capture it further, here is a heat map to particularly segregate it based on the sectors. So if you look at a particular entry in this heat map, let's say this one over here. So T is the trading sector here, M is the manufacturing metal sectors. So this particular cell here shows out of all the edges coming out of this particular sector T, what fraction of them ends in the manufacturing metals sector. Let's say you pick this one. So this one shows out of all the edges emanating from the finance sector, how many terminate in the business sector. So what we see here is that almost all the sectors, they have a good fraction of ties which are ending in the manufacturing metals and the business sectors. So for the further analysis, we also try to see what is exactly the sector-based assortativity of the network. So since the connections are not based on sectors, this is the number is very less, only 0.04. We also computed the assortativity based on registration state, which is also less, 0.2. However, this doesn't mean that there isn't a community structure in the network. So when we applied community detection algorithm on this network, we obtained the modularity score, a significant modularity score of 57%, which shows that there are communities in the network and there are companies forming communities. But as of now, we haven't been able to find the reason behind this homophily. So what actually is causing it. So that is one of the directions for the future work. At the end, we also studied some sector-induced subgraphs to see how the landscape, corporate landscapes in various different sectors differ. And for most of the networks, since there are not enough intra-sector ties, if you draw an induced subgraph on the companies of that particular sector, the network falls apart. It doesn't have that high number of edges. So apart from these five sectors, manufacturing metals, manufacturing equipments, manufacturing wood, business, and finance. So all these five sectors, they retain a significant induced subgraph. So these are some of the properties. And if you look at their giant component, again, it is not very big, but yeah, significant as compared to the other sectors. Their diameters are very large and average path length is low. So just to show the comparison, on this left hand side is the induced subgraph of manufacturing metals, which is MMP sector. So as you can see, the giant component is very well visible over here. And there is a significant structure in this particular graph. On the other hand, if you see the same induced subgraph for the trading sector, it actually falls apart. So even there is no giant component, it's mostly a disconnected graph. Mm. So that calls for further work, but what we have shown over here is that the if you look at particular sectors, the corporate landscape in different sectors can be very diverse based on what kind of policies are used there. So that is the analysis that we have done so far. It's the final conclusion slide. So so what we have observed is the absence of an inner circle. So if you look at the most central directors, they are not that well connected to each other. If you look at the sector-based analysis, so based on sectors, the assortativity is very low, but the network of the companies still show a very high modularity. So that is one area for potential work. And another future direction that we wish to pursue is a longitudinal analysis. So as of now, we have studied this entire network as one single snapshot from 2004 to 2018, but definitely a broader time-based analysis can be done. Thank you so much.